Hello dear friends, welcome once more to another video in our YouTube channel. In this video friends, we shall be looking at the correction of the Cameroon Advanced Level Physics June 2024 section A. So guys, stay connected, watch the entire video from start to finish guys. Don't miss out on any part of this video so you can understand every bit of the concept we shall be discussing today. So friends, if you're new to our channel friends, don't forget to subscribe to the channel, because that is the only way you stay updated to all the latest updates we upload on this our channel on daily basis guys. You can only have access to all our great contents guys once you have subscribed to the channel. And friends, if you are able to have access to this video today friends, means you are so special. You need to extend a hand of fellowship to your friends by simply sharing out this video with them friends. Please share the link to this video with them, or the link to the entire playlist where you found this video to them, so they can watch and score their own good grades in their examination guys. Thank you very much. If you're new to our channel guys, the only way you can get access to all our contents guys is by subscribing to the channel, liking the video guys. Place a comment in the comment section down below if there's something that I'll be doing in this video that you don't understand guys. Make sure you let me know in the comment section down below so I can get back to you to make you understand, explain the concept so well back to you as soon as possible. Okay guys, I think we should get started. But before we get started guys, I'm going to keep a link to our WhatsApp group in the description of this video for your convenience guys. Visit the description of this video guys to find the link to join our WhatsApp group. Okay guys, let's get started. Okay friends, the question 1 of that particular question was saying that figure 1 shows a current carrying solenoid wound on a steel rod. This is it. Now they're saying that from Biot-Savart's law, it can be shown that the size of the magnetic flux B inside the solenoid is given by B equal to mu 0 Ni, where that's B equal to mu Ni, where mu is the permeability of the medium, N is the number of turns of the coil per unit length, and I is a current in the solenoid. Now A, draw a diagram to show the magnetic flux pattern of the solenoid B. Using only units, show that the above equation is homogeneous, and C, if the steel has a relative permeability of 2000 and the above solenoid has 250 turns, to determine the magnetic field strength inside the solenoid. Okay guys, let's get started. We need to have it in mind friends that the magnetic flux pattern around a solenoid guys is similar or is identical to that of a bar magnet. Okay, this is going to be a solenoid guys. So friends, as we all know guys, the magnetic flux pattern is going to be of this form, going to be like this friends, like this. So I have simply sketched the three-dimensional view of the magnetic flux pattern. But guys, you need to note that these our lines in blue friends are what the magnetic field lines, right? And one property that you must take note is that the field lines should never intersect each other. Okay, they should never cross or even intersect each other. So when drawing it friends, please make sure that they shouldn't intersect each other. You're seeing mines are intersecting because I have drawn but the three-dimensional view. Okay, these lines are not supposed to intersect each other. Okay, now guys, the magnetic field lines, as you all know guys, is a vector, meaning it has a magnitude, it has a sense, it has a direction, and it has what guys, a point of application. So we need to insert the direction of this magnetic field line guys, and we know that it always leads from the north to the south, right? Another question guys, which of these ends is the north, which end is the south? Now what can help us to know which end is the north, which end is the south friends, is simply the Maxwell's right hand thumb rule, or the right hand grip rule, which is simply saying that that we should simply insert our right finger guys. We should happen to grip that solenoid with our right finger such that the thumb points in the direction of the north pole. Then the alignment of your fingers guys tells the direction of flow of current. So if you look at this, our solenoid in this case guys, the current flows inward, right? So it has to be flowing like, it flows like this upwards, like that guys. So this is the direction of flow of current. it flows upwards, guys. That's how it flows, right? Great. Okay, now guys, according to our right hand grip, which is basically that we should grip this our solenoid like this, such that the thumb, the direction of this our thumb, guys, tells us that what this is the north pole, right? Then do you see that the fingers are aligned in an upward direction? The fingers are pointing upward, right? These are fingers are pointing upward. That's direction of flow of current. It means that this thumb direction tells us what, that this end is the north, and this end, guys, by default is the south, right? As such, guys, once we must have done this, now we can therefore come back to our fields and insert their direction, since they are from the north pole to the south pole. So we have to insert like this, from the north to the south. We do the same thing on all of them, guys, from north to south. Great. So guys, that's how we can answer this question. That's how we can answer it. So guys, if there's something you don't understand, friends, please let me know in the comment section down below, guys. I'll get back to you as soon as possible. Make sure you are subscribed to this channel, friends, to have all our latest updates, to have all the contents in this channel. If on the day of the exam, friends, please don't draw this hand, okay? Don't draw this finger. I just happen to draw it because I want to illustrate to you guys what the Maxwell's right hand thumb rule is simply saying. Okay, that's the first part. I think it was for 3 marks. Okay, it was for 3 marks. Okay, now the B, if not 2 marks, guys, it's for 3 marks. The B part reads that using only units to show that the above equation is homogeneous. Okay, now guys, this is the equation that we have, B equal to mu ni. Now friends, you know that if this our equation is homogeneous, it therefore means that the units of B has to be equal to what, guys? The units of mu ni. Now guys, from our formula, F equal to B I L, that's from the force produced by a current carrying conductor placed in a magnetic field such that the length of that conductor is L. It therefore means that guys, if we make our B the subject and take the units on both sides, we're going to have the units of F to be the same as what, guys? Kilograms meters per second squared, right? Because units of B equals what? Units of F over L. But units of F is equal to kilograms meters per second squared, from F equal to MA. Then guys, the units of I is simply equal to what, guys? It's simply amperes. L is length, right, which is simply in meters. So that's why we have AM. Then now guys, now that we have this, now we can therefore at this point now, guys, say that our unit of B is equal to what, guys? Kilograms meters per second squared over AM. That is IL. We have that. So doing that, we are going to have units of B to be same like kilograms per second squared per ampere, because this M and this M, they can cancel. Ampere goes up as ampere raised to the power -1. Great. So guys, that's it now. Then friends, at this point now, we need to get the units of mu, right? So from the formula, F equal to mu0 I squared L over 2 pi r, wherefore in this case now, guys, our mu0 is a permeability of free space. R is simply what, the current, right? And our L is simply what, guys? The length of the conductor. R is the separation between the two identical conductors that carry the same amount of current. So in this case, friends, if we make mu0 the subject and take the units on both sides, we're going to have the units of mu0 to be the same as the units of Fr over 2 pi I squared L. So in this case, guys, the units of F, we all know, we simply plug in everything. But we should have it in mind that mu is a permeability of this medium, right? While mu0 is a permeability of free space, so they both have the same unit. This means that the unit of mu is the same as we have the kilograms meters squared per second squared over A squared M. So simplifying that, guys, give us the units of mu to be same like we have the kilograms. So we have 1 meters cancels 1 up. We have meters per second squared per ampere squared. Great. So guys, at this point now, we can see that the unit of mu and I is the same like we have the kilograms per second squared amperes -2 into that of n, guys. Keep in mind that n in this case is the number of turns per unit length, or the turn density. So the unit is per meter. So we have this, then we have amperes. If you simplify, guys, we have kilograms per second squared per ampere squared. Great. So guys, if you look at this so well, you can see that the units of mu and I is equal to what? we have kilograms per second squared per ampere, right? And if you look at the unit of B in this case that we found B to what, guys? The unit of B to what? Kilograms per second squared per ampere. So now, guys, since the unit of B is the same like what the units of mu and I, we can conclude that this our equation now is homogeneous. Great. So friends, once you are able to show that the unit of B is equal to unit of mu and I, therefore means that you've shown that the equation is homogeneous. Note that an equation is just be homogeneous from our step here if the unit of B equals the unit of what? Mu and I, which we have just proven it just here, because the unit of B is kilograms per second squared per ampere, and we have ended up with the same unit here, so it is homogeneous. Okay. Now the next part is saying that if steel has a relative permeability of 2000 and the above solenoid has 250 turns, we should determine the magnetic field strength inside the solenoid. Okay, so they want us to get the value of B. So now friends, you notice that they've given us the relative permeability, right? So we need to get the permeability inside this our steel rod, but we know that the permeability of a medium is related to the relative permeability and the permeability of free space by the equation mu equals mu 0 mu r, where our mu, guys, is the permeability of a medium, which in this case is that of steel. Then mu 0 is the permeability, friends, of free space. Then mu r is the relative permeability. So in this case, guys, if we replace our mu in this case by mu 0 mu r and substitute all of the value, guys, we're going to have our B to be the same as mu 0, guys, has a value from the formula booklet, guys, to be given as 4 pi times 10 raised to the power negative 7. Then mu r has been given to us as 2000. Then friends, n in this case, guys, is the turn density, namely the number of turns divided by the length. The number of turns is 250. The length is 35.2 centimeters, which can put that to meters, which becomes 0.352. Then friends, our I in this case, friends, is the current. So we have 10.5 amperes. So this is what we have. If you substitute, guys, and simplify, we have an answer of B to be the same like 18.74 teslas. Okay, so guys, this is the answer that we get. That's how we can answer this particular question. All right, so friends, that's for question 1, guys. If there's something that is unclear to you, friends, please let me know in the comment section down below, so I can explain to you further as soon as possible. Okay, guys, let's go to question 2, guys. Are you ready? Let's go. Okay, the question 2 reads that copper has about 8.49 times 10 raised to the power 28 charge carriers per unit volume and a resistivity of 1.68 times 10 raised to the power negative 8 ohm meters. In figure 2, a copper cable with a cross-sectional area of 0.27 millimeters squared is connected in series with a battery. The connecting cables have negligible resistance. A. If the ammeter reading is 6.0 amperes, determine Roman 1 the drift velocity of the charge carriers. Okay, guys, let's start with this. So friends, in order for us to get this question done, we need to know how the drift velocity, guys, is related to the number of charge carriers per unit volume, the charge of the material, the drift velocity, guys, and the cross-sectional area. It is related by the formula I equal to never. Okay, I always want to know the formula as I equal to never, because it just makes it being a mnemonic for me to always recall. So we have I equal to never, where I in this case is the current, N is the number of charge carriers per unit volume, E is simply what, guys, the charge on the material, V in this case is the drift velocity of the electrons, then A, guys, is simply the cross-sectional area. So since the question wants us to get the drift velocity, guys, it therefore means that our V in this case is therefore going to be I over NEA. Putting in all the values, guys, we're going to have V to be the same like I is 6. I in this case has been given. Oh my god, where's I, friends? Let's look at I. Let's see I, friends. That is 6.04 amperes. That's what we have. Then our N, guys, the number of charge carriers per unit volume, that is 8.49 times 10 raised to the power 28. Then friends, our E in this case is the elementary charge of an electron, which is 1.6 times 10 raised to the power negative 19. Then our A cross-sectional area, guys, is simply equal to what? 0.27, right? Which is millimeters squared. But we have to convert millimeters squared to meters squared. So if we do that, guys, we simply need to do what? We simply need to, since the prefix milli stands for 10 raised to the power negative 3, if we replace milli by 10 raised to the power negative 3 and we square that, we are going to have 10 raised to the power negative 6. That's why we have negative 6 here. So simplifying, guys, we have V to be the same like 1.65 times 10 raised to the power negative 3 meters per second. Okay. The next part is saying that we should get the reading of the voltmeter. So the voltmeter, guys, simply reads what? The current, right? The current that flows in this circuit. So we need to recall that the resistivity is related to the absolute resistance and the length as well as the cross-sectional area by the formula R equals rho L over A, where R in this case is simply the resistance of the copper wire. Then rho is the resistivity of the copper wire, L is the length of the wire, and A is a cross-sectional area. So it means that our if we make, since we know that our V from Ohm's law is given as IR, where V is the potential difference across the cell, I is a current, R is a resistance. It all means that if we replace this our resistance capital R by its value rho L over A, means we're going to have our V to be the same like I. This I, R is what, guys? Is rho L over A. So we are going to have this. If we plug in all the values, guys, we're going to have V to be the same like I is 6.04. Our rho is 1.6 times 10 raised to the power negative 8. L is, in this case, is 752 centimeters, right? Putting that to meters by dividing by 100, we have 7.25. Then our A cross-sectional area, guys, as we have here, when converted to meters squared, we have 0.27 times 10 raised to the power negative 6. Simplifying this, guys, give us our V to be same like 2.72 volts squared. So, guys, that's it. Always learn to respect significant figures, okay? Let's respect significant figures, because if you look at the smallest significant figure here, guys, is to 2 significant figures, right? That is 0.27, 1.68, 8.49, and so on, guys. So we have to put it to two significant figures. Okay, that's it, guys. That's it. Don't forget to subscribe to the channel, friends. Turn on your bell icon to get notified each time you upload new contents. You will be the first person to get notified. The B part reads that explain why the reading of the voltmeter increases when the switch is open. Okay, now, guys, you need to agree with me that when this our voltmeter is being connected across this our cell, right? Do you see that the voltmeter in this case measures what? The EMF of the cell, right? Not just the EMF of the cell, guys, but there is a potential drop across this our wire, since our wire has some resistance. Okay, it has some resistance, so some potential difference is going to be dropped across the wire, such that whenever this switch is open, now it never means that this our circuit that has the wire becomes an open circuit, means no potential difference is dropped now across the wire, means that the voltmeter now measures just the EMF of this our cell, which always has a maximum value. Okay, so what I'm saying now is that, guys, the switch becomes on, friends, the voltmeter reading is going to increase, because now it never measures now the full voltage of the battery alone without any voltage drop across the copper cable. Note, guys, note that with this copper wire in place, guys, is going to have what? Some resistance, right? And consequently, the potential difference that this guy is going to measure now is going to be the one that is being dropped across the wire as well. But when the switch is open, right, it never means that there is no resistance of this wire, right? Since this circuit becomes an open circuit now, means the voltmeter now in this case measures just the EMF of this our battery, which obviously is going to increase because there is no potential drop across this one as well. No potential difference is going to drop. No potential difference is going to be dropped, friends, across this our wire when the switch becomes open. Okay, that's it. If you don't, so guys, if you've not understood this particular concept, friends, please let me know in the comment section down below, guys, so I can explain to you, especially as soon as possible. Okay, that's it, guys. That's it. Let's go to question 2, friends. Let's go. So, friends, question 3 reads that figure 3 shows a break wall of thickness X and surface area A The heat entry in the inner wall is Q1 at temperature T1, and that leaving the outer wall is Q2 at temperature T2. So this is what we have, guys. This is it. Then now the next part is saying that we should state two conditions for heat conduction through the above wall to have reached a steady state. Then the B part should define temperature gradient and write an expression for it for the wall above. Okay, guys, I think we should tackle those parts. Okay, now guys, we need to know that when steady state has been attained, right, there are two conditions necessary. One, the amount of heat that is entering Q has to be equal to the amount of heat that is leaving this our wall at Q2, right? So in essence, what I'm saying is that Q1 has to be equal to Q2 when steady state has been attained. Okay, that's the first condition that you should say. And now, guys, the temperature difference between the inner surface and the outer surface, guys, have to be constant when steady state has been attained. So the first point, guys, we can see that the temperature difference between the inner and outer space of the wall, guys, must remain constant over time. And secondly, guys, the amount of heat entering the wall, that is Q1, has to be equal to the amount of heat leaving the wall, Q2, ensuring that no heat is stored within the wall. Great. So guys, this is just this second part simply talks about the conservation law. Okay, it is a conservation law. Okay, now guys, the next part wants us to define temperature gradients and write an expression for it for the wall above. Okay, so guys, temperature gradient simply refers to the rate of heat flow with distance in a body. Okay, the rate at which heat flows in any body, guys, with distance. So that's how you can define temperature gradient. That's it, guys. And an expression for it, guys, can be given as Q over T, which is equal to Ka delta theta over X, where for our Q over T, for instance, is simply the temperature gradient in this case. Our K is what the thermal conductivity of the material we are talking about, which in this case is the wall. Then A is the cross-sectional area of the wall. Delta X in this case, delta theta in this case, guys, is simply what the difference in temperature, right? Then X in this case, guys, can be the thickness, which we are talking about in this case, or it can still be the length of the wall. It depends on how heat flows. In this case, heat flows horizontally, right? So our X in this case is simply what the thickness of the wall. But assume a case where for heat flows vertically. So our X in this case, guys, is going to be what, guys, the length of this our wall. But in this case, X is the thickness of the wall. Okay. Now the next part wants us is saying that if the wall is 12 centimeters thick, that is X, 12 centimeters thick, with heat flow surface of 0.08 meters squared, and it's made up of bricks of thermal conductivity of 0.8 watt per meter per Kelvin, we should determine the thermal resistance of the wall. Okay, so guys, the thermal resistance, guys, by definition and from its formula, for instance, is simply given as R to be the same like X over Ka. Okay, that's the reciprocal of this our quantity in yellow. X over Ka means our X in this case, guys, is 12. We have to put that to meters times 10 raised to the power negative 2 meters over our K in this case, guys, is 0.8 watt per meter per Kelvin. Then our A in this case is 0.08 meters squared. Simplifying that, guys, give us an answer of 1.875 watt. That's 1.875 per watt Kelvin. Okay. Then now, friends, the next part is saying that hence or otherwise calculate the rate of heat flow through the wall if T1 is 355 Kelvin and T2 equals 330 Kelvin. So friends, if we look back at this our formula, right, we can see that our Q over T is equal to what? Ka over X times delta theta, right? So it means that what is Ka over X, guys, is simply what the reciprocal of what? Of our resistance, right? So we can write this one as Q over T to be the same as our temperature. That's the change in temperature, which is simply the difference between this and that, which is 25, over now we divided what with the thermal resistance. So in this case, we are going to have an answer of 13.33 watt. Great. So guys, that's the answer. That's it. If there's something that is unclear to you, friends, please, I owe you the clarification, guys, for you to let me know in the comment section so I can make you understand the concept as soon as possible. Okay, let's go to question 4, guys. Let's go. Okay, guys, the question 4 reads that we should define simple harmonic motion. The B part is saying that figure 4 shows how energy E of a simple harmonic oscillator varies with displacement x from the equilibrium position. So this is the graph, guys. This is the graph. So friends, you've seen that I've designed this graph right. I've drawn the graph to be very visible and very clean for you guys. So make sure you subscribe to this channel, friends, and like the video. Please share the video out with your friends, guys. That's the way in which you are appreciating what our academy does. Okay, now the Roman one is saying that we should state with reasons whether E represents total mechanical energy, kinetic energy, or the total energy of the oscillator. Then the Roman 2 is saying that if the oscillator has a mass of 30.0 grams, we should use the graph to determine its frequency of oscillation. Okay, so guys, simple harmonic motion, guys, is simply the periodic motion of an object whose acceleration is directly proportional to its displacement about a fixed point and is always directed towards that point. Great. So guys, that's simple harmonic motion. It has to be what, guys? A periodic motion of an object whose acceleration is directly proportional to its displacement about a fixed point and is always directed towards that point. Great. That's how you can define it, guys. And this definition was for 2 marks. You have all the 2 marks. Okay. So this is the graph they've given us, a graph of energy against displacement. So friends, what do you think this graph represents? Is it total energy, mechanical energy, or kinetic? So friends, obviously this graph also represents the kinetic energy, okay? Because the kinetic energy, friends, is maximum at the equilibrium position. That is at the point where our x is 0. So when x is 0, you said the graph has a maximum value. Right, great. So this is a graph of kinetic energy. Great. And that's the reason, guys, because it is maximum at the equilibrium position. So that's it. Now the question is saying that that if the oscillator has a mass of 30.0 grams, you use the graph to determine its frequency of oscillation. Okay, so guys, in order to get this question, so many people might get stuck when they reach at this point, friends, because maybe their physics might be so limited. But you can simply use what you have, friends, to get what you want. This is what I'm talking about, guys. We know that even from our normal mechanics, we know that our kinetic energy K is giving us what? 1/2 mv squared, right? So but we know that our V is giving us what? Omega r, right? Where omega in this case is simply the angular frequency or the angular velocity. Then r is what, guys? Is the radius, right? It's simply the radius or the displacement. So if we take our V and we substitute into this our equation, guys, we're going to have Ke to be the same as 1/2 m omega squared r squared. Means, friends, if we make omega the subject of this our formula, we have omega to be the same as the square root of 2 times the kinetic energy over mr squared. But friends, let's recall that the frequency is simply given as f to be the same as omega over 2 pi. So since our omega is this, if we substitute everything, guys, we are going to have our frequency f to be the same like 1 over 2 pi into the square root of 2 times Ke over mr squared. So if we plug in all the values, guys, notice that if you look at your kinetic energy at this point, guys, look at your Ke at this point, you can deduce that your Ke at this point, friends, is about 74, right? Because if from now, if you look at what each square represents, you see that each square represents 10 units, right? 10. So here has what? Here has to be 70. So if you look at the actual graph, just that this one is not drawn so much to scale, you see that your E in this case is 74. but the energy, friends, E is in millijoules, right? We have to convert that to joules by multiplying by 10 raised to the power -3. And also your displacement R is what, guys, is in guys, it's also in millimeters, right? So oops, guys, if you look at what I've done here, friends, you see that this R was supposed to be squared, right? It hasn't been squared here. So friends, please make that adjustment. Please make the adjustment. You notice that let me see, just simply make the adjustment here. Okay, make the adjustment here. Make sure you square this 11.5 times 10 raised to the power -3, all that squared. Okay, just try to square it, then you punch. This is the answer in which I have when I haven't punched, when I haven't squared. So please try to square it, then you punch. You're going to have an answer different from this. Okay, you have this place. So this is the frequency in which I have, but it isn't correct. Okay, please make sure you square this quantity. Square this 11.5 that times 10 raised to the power that. Okay, square it before you punch. Okay, that's it. Okay, I believe the concept is clear, right? So if the concept is not clear, friends, you know what to do. Make sure you reach out to me in the comment section down below. Okay, let's go to question 5, guys. Are you ready? Let's go. The question 5 reads that according to the kinetic theory, the pressure of an ideal gas is given by P equal to 1/3 rho C squared bar, where P is the pressure of the gas, rho is the density, and C squared bar is the mean square speed of the molecules. A. State 2 assumptions used to derive the equation. B. Use the above equation to show that C squared bar is related to the absolute temperature of the gas by C squared bar equal to 3 RT over M. Okay, where R is the molar gas constant, T is the absolute temperature of the gas, and M is the molar mass of the gas. Okay, guys, let's start with the first part. So there are up to 4 assumptions of the kinetic theory, guys, up to 4, but this question is asking for just 2, right? So the first one is going to be that the volume of the molecules, guys, is negligible compared to the volume of the gas. Then the second one, guys, is going to be that the duration of each collision is negligible compared to the time lapse between collisions. You can also say that collisions, friends, are perfectly elastic. That is between the molecules and the walls of the container are perfectly elastic. Or you can simply talk about the issue of time as well. Yeah, but these two, guys, are okay. These ones are okay. Then the next part is saying that you should use the above equation. You should use this above equation, guys, to show that C squared is equal to that. Okay, guys, this is no big deal. So that's the equation P equal to 1/3 rho C squared bar. So friends, let's look at rho, guys. What is rho? Rho is simply what the density, right? Let's keep in mind that there are infinitely many molecules in that gas. So let's say if our capital M, guys, is the mass of each molecules, it never means that what there are n number of those molecules, right? So we are going to have a total of nm over v density. Okay, so this nm is simply the total mass of n molecules that are present in that container. So we have nm over v, which is simply equal to what? The density. Okay, so in this case, guys, if we multiply all through by v, guys, do you see what we're going to have PV to be same like 1/3 nm C squared bar? That's what we have. So guys, in this case, where our capital V is simply equal to what? The volume of the container. Now, guys, we also know that our PV is equal to nRT, right? That is, we know this formula so well, right? The formula from the kinetic theory of ideal gases, we know that PV is equal to nRT. So it therefore means that, guys, we can simply equate, since PV is equal to nRT and this in PV is equal to what? 1/3 nmc squared bar. We can equate these two. Since PV is equal to that and this in PV is equal to this, means nRT has to be equal to what, guys? 1/3 that, right? So 1/3 nmc squared bar has to be equal to what? nRT. So our n can cancel on both sides. If we multiply it all through by 3 and divide all through by m, we are going to have c squared bar to be same like 3RT over m, guys, as required. That's it, guys. That's the proof. That's it, as required. Great. Okay, so this is what we have now. The next part simply is saying that the root mean square speed of a certain gas is 850 meters per second at room temperature of 30 degrees Celsius. You determine the root mean square speed of the molecules if the gas is heated to a temperature of 150 degrees Celsius. Alright, so let's dive straight into it, friends. Notice that we can write this our c squared to be the same like 3r over mt, right? So in this case, our r in this case, guys, is a constant. M as well is also a constant, right? So we can see that our c squared is directly proportional to what? T. What does this mean, guys? It means that our c1 squared over t1 squared has to be the same like c2 squared over t2, which has to be the same as c3 squared over t2, and so on, guys. So this is what this statement simply means, okay, which is directly proportional. So in this case, since we are looking for our root mean square speed at this temperature, means we can make c2 squared a subject, which is going to be given as the square root of, we simply plug in the values. If we make our c2 squared the subject, guys, we are going to have c1 squared, which is 850 squared, over t1, which is 300 and which is 30, right? But we have to convert this our temperature to from degrees Celsius, guys, to Kelvin. So we have 303 Kelvin. Then converting this one as well to Kelvin, we have 422. If we simplify that, guys, we have our C2 to be the same. We have our C2, friends, to be the same as 1004 meters per second. Great. So, guys, that's it for the video, guys. That's it. Congratulations to all those who were able to watch the video up to this point, guys. Congratulations to you. If you found the content useful, guys, a simple thumbs up will mean the world to me, guys. Simply thumbs up the video, guys, by giving the video a thumbs up, guys. Like the video, guys. Importantly, subscribe to this channel and stay updated, guys. Subscribing to the channel does not mean that you're going to pay anything, guys. Everything that this academy offers is totally free of charge, just your subscriptions. And please share this video out with others. Share it out with them, guys, so that they can have access to great and important content like this, which has a very great role to play in their success as well. Great. So, guys, I am Omenjo Makaras, guys, and this is Humble Mak Academy. Have a blessed day.